Here we are standing atop the Fremont Bridge in downtown Portland over the Willamette River. The Fremont Bridge was constructed in 1973. The main arch section is a little over 2,000 feet long, and it consists of a top deck and a bottom deck. The top deck carries southbound I-405 traffic. The bottom deck carries northbound I-405 traffic. The top deck of the Fremont Bridge is what's called an orthotropic steel deck. It consists of half-inch thick steel plate with ribs underneath it. The orthotropic steel plate looks similar to cardboard in that it's got a flat panel on top and corrugations underneath it. And that's what carries a majority of the load of all the traffic that drives across the top of the deck. On top of this steel plate is a layer of epoxy asphalt with another thin layer of regular asphalt on top to serve as a wearing course that could take the damage from studded tires and heavy truckloads and could be replaced easily. The epoxy asphalt was intended to last as long as possible, and the goal was to last upwards of 40 years. Well, the epoxy asphalt lasted quite a while and is now nearing the end of its lifespan. So this project is intended to come along and replace all the original epoxy asphalt on this bridge deck with new epoxy asphalt. This new epoxy asphalt is a newer generation of material, been 30 to 40 years of refinements since it was first used. So we intend this bridge deck to last at least, or hopefully longer, than the original epoxy asphalt. The view from this overhead camera is from the center and the top of the arch, looking one direction, and as the work completes to the center of the bridge, the camera rotates to look at the other half of the bridge. Placing the epoxy asphalt is a unique process that isn't very familiar to people in Oregon, particularly ODOT. The last time ODOT's had experience placing epoxy asphalt was on this bridge when it was constructed in 1973. The epoxy asphalt is very similar to regular asphalt, but with some significant differences. In addition to the oil or binder that goes into the aggregate to make asphalt, included with that is a two-part epoxy mix, a part A and a part B. The epoxy is a thermoset product that sets and gels with heat and time to create a very hard, strong, durable surface, much more durable than regular asphalt. The product for this project comes from a company called Chemco Systems out of California. In addition to the epoxy asphalt, there's layers of what we call epoxy bond coat. That's a spray-on product that acts as the glue that holds the epoxy asphalt to the steel deck, as well as we put it between layers of the epoxy asphalt. Our project calls for placing two layers of epoxy asphalt, a base lift and a top lift. And the epoxy bond coat goes between those two lifts as well as on the steel deck. The epoxy bond coat is a very strong, very durable product intended to reach strengths of around 300 psi pull-off strengths. Will really help this epoxy asphalt adhere to the steel deck. ODOT's plan was to do full closures of the Fremont Bridge. Removal of the old material really required a lot of equipment and a lot of manpower to remove the epoxy asphalt. So really in the best interest of the traveling public and the worker safety, we really needed to close the bridge fully to traffic on the top deck. So we plan to do that over a course of 3 weekends of fully closed and 1 weekend partially closed. And the partial closure happened the first weekend, and that was where we worked on just the left shoulder of the freeway. The next 2 weekend closures took care of the remainder of the bridge working its way across. The process of replacing the asphalt with new epoxy asphalt first started with the removal operation of the existing asphalt, having to mill and grind off as much of the existing asphalt as we could without damaging the underlying steel deck or the bolts and splice plates that tied all the steel plates together. After they ground off as much as they could, and then the operation started with excavators and jackhammers and other laborers to chip away and pull off all the remaining asphalt. All the old asphalt had to be taken down all the way to the bare steel deck. The process of removing that epoxy asphalt, the old epoxy asphalt off the bridge deck, was very painstaking. The contractor had a labor force upwards of 40 people, doing everything from operating the equipment to laborers using hand equipment and chipping around every single bolt in the splice plates on the steel deck. We estimate there were over 56,000 bolt heads that had to be cleaned around. Each of the bolt heads has 6 faces, and each face had to be chipped off, cleaned, and basically taken down to bare steel, bare bolts. In order for this new epoxy asphalt to stick and adhere as best as it could, we had to make sure all the old asphalt, all the old debris, everything was off of there, so that we had a nice clean steel surface for the epoxy asphalt and the epoxy bond coat to stick and adhere to. We want to get the best product we can so it will last as long as it can. In the process of removing all the asphalt, we found some areas where the deck had been damaged prior, either through repairs or maybe when it was first installed, and we tried to take the time we could now to repair some of those areas in the steel deck, some grinding and some welding on some of these areas. For the left shoulder, our intent was to give the contractor the opportunity to experience and see how rigorous the removal operation would really be, how much effort it would take. Once that was completed, for the next 2 weekend closures, ODOT's plan was to do the east half of the bridge, and then the second weekend do the west half of the bridge, fully taking the asphalt off and repaving it. Now our requirement was all that work had to be done over the weekend and had to be completed by 5 a.m. on Monday morning. The bridge absolutely had to be reopened by 5 a.m. on Monday morning for the normal commuting traffic. The weekend closure started at 11 p.m. on Friday nights and ran through 5 a.m. on Monday morning. During that time, the contractor had to remove all the existing asphalt, clean the steel deck, spray the epoxy bond coat, place 2 layers of epoxy asphalt, restripe the bridge, clean everything up, and reopen the traffic at 5 a.m. on Monday. So ODOT's plan was to do 2 full weekend closures, east half of the bridge and west half of the bridge on separate weekends. The contractor came to us with an alternate proposal that they felt would better suit their operation and could be done in a shorter amount of time than ODOT had planned. Instead of doing the east half and west half of the bridge, the contractor asked to do it lane by lane. So the first weekend, do the 2 left lanes, the next weekend, do the 2 right lanes and the final right shoulder. The contractor's proposal to change to doing it lane by lane instead of half by half was based on the ability for them to make a continuous operation from one end of the bridge to the other and not have to stop and bring all their equipment back to the end again and just to do half a bridge. What it meant was less downtime, less setback time, and they could get the asphalt done in a quicker amount of time. Also, as part of ODOT's plan, between the first partial closure of the left shoulder and the next 2 weekend closures, we needed to remove some of the weight from the bridge. The asphalt constituted a pretty significant weight on the bridge. There were upwards of 3,000 tons of asphalt on the top deck of the bridge, existing. Arches can be very sensitive to unbalanced loading. Too much weight on one end versus the other can affect the structure more than we would like. So ODOT's plan was to come in and try to remove the top 1.5 inches of the existing asphalt, remove that from end to end of the bridge to help reduce weight on the bridge. That way, when the contractor came in to remove the rest of the asphalt down to the steel deck, there was less weight overall and it reduced the amount of unbalancing on the arch. So the contractor did that over the course of 4 weeknights, having an available 6 hours each night to work. The contractor came through and ground off the top 1.5 inch layer of the asphalt in preparation for the first weekend closure. So after the contractor removed all the existing asphalt and chipped around all the bolts and got everything as clean as possible, we had to do a final operation to clean the deck and also to provide a nice textured surface for the new asphalt to stick to. So that was done by a process of shot blasting the steel deck with 2 mobile shot blasters. The 2 mobile shot blasters have blasting heads about 30 inches wide, and they can travel along at varying speed and shoot very small, tiny steel shot at a very high speed at the steel deck to remove any latents or residual oil or film or anything that's left on the steel deck, and also provides a little bit of surface texture onto that steel for the spray bond coat and the asphalt to adhere to. Now you can see as these shot blasters move along the deck, if you look behind them, you can see how much different that steel deck looks from in front of it. It's removing quite a bit of just leftover, very fine material that the excavators and manpower couldn't remove. After the steel deck receives the shot blast treatment, the contractor has 6 hours to start spraying the epoxy bond coat. That 6-hour time limit is there to prevent the steel being exposed to the elements longer than it needs to. If it's exposed too long, just the humidity in the air can start causing small amounts of rust to form on the steel. So the 6-hour requirement is there to prevent that from happening. And the epoxy bond coat is applied by a spray wand done by hand. And as you can see, the spraying operation does create a mist. So along the sides, workers move along with wooden screens to protect overspray from leaving and spraying the asphalt or the steel deck next to it. Once the epoxy bond coat is sprayed, it is a very viscous product, but it is kind of slippery. So for the next operation, when the paving machine lines up to start paving the epoxy product, you can see workers shoveling epoxy asphalt out of the bed of the paver and spreading it on the ground in front of the paver. That's intended to provide traction to the paving machine in the slippery epoxy bond coat. So the epoxy asphalt is being produced by a company called KF Jacobson, and their asphalt plant conveniently is located right below the bridge, and so they have a very quick haul to the project from the plant. Even with that, the product is very sensitive to temperature and time requirements. In fact, our specifications have some very rigorous time limits on how much time the asphalt needs to sit in the truck before it's placed, but also it needs to be placed within a certain time frame as well. And it's all dependent on temperature of the mix. If the temperature is a little bit hotter, the contractor has less time to place it. Epoxy asphalt is different from regular asphalt in a respect that it's not produced as hot as regular asphalt. The epoxy asphalt is produced around 230 to 250 degrees Fahrenheit, whereas regular asphalt is produced over 300 degrees. The epoxy that's introduced into the asphalt needs heat and time to start the chemical reaction to make it start to set and harden. That's why we require the asphalt to sit in the back of the trucks for a set amount of time, so that lump of mass of asphalt, that hot asphalt, can initiate and start the chemical reaction of the epoxy. So the hotter the asphalt, the quicker the reaction will go. After the asphalt's produced and placed in trucks, they insert long stem thermometers in the side of the truck. So as the truck travels to the bridge site, those thermometers start reading the temperature of the mix inside. Once it arrives at the bridge site, we monitor the readings on those 3 thermometers, average them out to get a single reading, and that determines how long that load of asphalt needs to set. If the truck doesn't dump its load within that window, the asphalt will lose its workability to be able to be placed and compacted, so that truckload will get rejected. Each truckload is about 12 tons of asphalt. The asphalt's made in batches, and each truckload holds about 3 batches of asphalt. And to go along with other requirements we have for the contractor to produce the mix, they've got to make those 3 batches within 7 minutes. If it takes longer than that, there would be too much variability in that truckload, so we would have to also reject that load and throw it away. Our designers intended for the epoxy asphalt to be placed in 2 lifts. The first lift is a leveling lift because of the bolt heads that stick up on the steel plate. Because those bolt heads stick up on the steel plate, this first course of epoxy asphalt ends up being a leveling course to kind of level out over those bolt heads and make sure we can get a smooth product over those. Then on top of that, we place a top lift to get us to the full thickness that we desire. In this case, our full thickness is 2 1/4 inches. The bottom lift, the leveling lift, is intended to be 1 1/4 inches thick, and the top lift is 1 inch thick. On top of the epoxy asphalt, we're placing a thin layer, an 1.5 inch thick layer of regular, what we call hot mixed asphalt concrete. And that regular asphalt lift is what we call a wearing course. And that's what's going to take all the loading from the trucks and all the studded tire wear. And that lift is intended to be a sacrificial layer, and that it can be replaced after it wears out and not have to replace the epoxy asphalt below it. It will take the majority of the brunt from loading, from traffic, and from studded tires. We've put down a little over 2,100 tons of epoxy asphalt, and we're going to put down approximately 1,400 to 1,500 tons of regular asphalt. All of the weekend closures have been completed on time. All the work that needed to be done each weekend was done. The project's been a great success.